Good evening once again. I'm Eric Walker, Chair of Highlands Astronomical Society, and I want to extend a warm welcome to HAS members and visitors from our North of Scotland sister astronomy clubs. Also, welcome to non-members, some of whom asked for our Zoom link right at the last moment. Nothing like having to live your life on the edge. I start off tonight with some sad news. As you most likely know by now, our oldest and one of our dearest club members, Arthur Milnes, passed away earlier this month at the ripe old age of 90 years old. I'm not going to dwell on Arthur's passing, except to say thanks for all the kind remarks and tributes we have received from you, which we have passed on to his wife, Lorna. Arthur will live long in our memories and also the ongoing working of our club. Now back to tonight. Tonight's timings. At about 20 to 8, we'll have our main talk, followed by a question and answer session. Round about 8:30, we'll have our club news, astro picks and targets for the month. And round about 10 to 9 probably, we'll have an opportunity for club members to make comments and questions and answers, and that will take us to the meeting close. There won't be any breaks during the meeting, so if you need to leave for any reason, just get up and go and keep yourself connected to the meeting. As always, we've been keeping our members and friends updated with emails, Facebook and Instagram links to various astronomy-related articles, events, and the many stunning pictures posted by you over the past month. It's great to see so many Milky Way pictures again, and also some early, if faint, northern lights. I'd like to ask you to please seriously consider joining Facebook and Instagram. Our club and many others throughout Scotland now use this as a main point of contact with their members. Our website is also kept up to date, but like all websites, you have to search through it to find what you want. Our observatory remains out of action due to the restrictions in place. However, I have some good news. Some very good news indeed. Last month, I reported that we had been unable to overcome the technical difficulties of webcasting live observing sessions at a quality high enough to make it enjoyable for the audience, or indeed the observing team. I am very pleased. In fact, I am ecstatic to report that we now have the means to webcast high resolution, high quality, live image observing of the night sky and of our sun. We can do it so that anyone with YouTube on their devices can watch and also live chat with us from anywhere in the world. You can be in your office, at the kitchen table, in the bath. You will be able to watch the Scottish Highlands night sky with us live. We are currently working on producing our first live webcast observing session, and we'll let our members and friends know when it's going to happen. Exciting news indeed, and a stunning achievement for a local amateur astronomy club. For your diaries, our next meeting is on Tuesday, the 6th of October, and it will again be hosted via Zoom webinar. Anyway, enough from me. I'm now going to introduce our main speaker for tonight, Professor Inika Demurto. Inika is a Belgian applied mathematician, having attained a master's degree at the prestigious Catholic University of Leuven in Belgium, and she now lives here in Scotland. She joined the hill walking and mountaineering student clubs in St Andrews and has actually finished all the Munros. Apart from that, she does quite a bit of sailing and qualified last year as a dinghy instructor. Inika lives in St Andrews, is married to Mark, who she met in the mountaineering club. They have their ups and downs, and they have 2 children, Thomas and Ben. Her husband, Mark, actually grew up in Aberdeenshire, so not too far away. Inika returned to Scotland as a PhD student in 1997, and in 2000, she was awarded a Particle Physics and Astronomy Research Council Fellowship, followed by a Royal Society University Research Fellowship in 2004. She was elected to the Royal Society of Edinburgh Young Academy of Scotland in 2011, and as a Fellow of the Royal Society of Edinburgh in 2015. Inika is currently Professor in Applied Mathematics at the University of St Andrews, as well as an Adjunct Professor at the University of Oslo, and also an Affiliate Scientist at the High Altitude Observatory in Boulder in the United States. She is part of the Solar and Magnetospheric Theory Group, and her research focuses on the dynamical processes and extremely high temperatures in the Sun's outer atmosphere, the corona. It is with great pleasure that I welcome Inika tonight, and here she is to talk about solar storms and atmospheric effects on Earth's communities. Over to you, Inika.
Thank you so much, Eric, for those kind words. It all made it sound very complicated. It just means I get to do a lot of traveling to nice places normally. So I'm going to share my screen just now. And I'm hoping that will work well. Okay, so hopefully that's worked well for all of you. And you can all see my title slide. So good evening, everybody. Thank you so much for joining this talk. I'm hoping to tell you something about our sun this evening, and I will just go on a little bit of a journey through the sun's atmosphere to end up with solar storms and the effect they have on us as living near this star. So let's start with something I am sure you all know very well. As a star, the sun is really quite boring. No astronomer is ever impressed when you tell them you're a solar physicist. It's an ordinary middle-aged star. We reckon we have about 4 to 5 billion years to go. It sits in one of the arms of our local galaxy. And the only reason the sun is a special star is, of course, because it's close to us. There would be no life on Earth without it. But for me as a solar physicist, it's the only star you can see in extreme detail. And I'm hoping to show you some of these images tonight, and you'll be equally impressed. So let's start at the very center, the solar interior. I'm sure everybody knows this, but deep inside the sun is the sun's core, where the nuclear reactions take place. The temperatures are extremely high, of the order of about 15 million degrees. As you move outwards then is the next layer inside the interior, which is called the radiative zone. Switch to the laser pointer here. The radiative zone takes up about another third, maybe a little bit more of the solar interior. And then above that, the last layer before you get to the surface of the sun is the convection zone. In the convection zone, as you can imagine, there's huge convection cells of hot material rising to the surface and then sinking back down again. When we come to the surface of the sun, the temperature has gradually declined here, and by the time we get to the surface, it's of the order of about 6,000 degrees. Now, of course, the sun is made of gas, so there is no real surface as such, but we have defined the surface as the layer of the sun that emits invisible light. Of course, because that's the light we can see as human beings. So there is no real surface there. There's just a layer we identify as the surface of the sun. So everything underneath this layer we refer to as the interior. Everything above this we refer to as the atmosphere, which is the bit that I'm going to be talking about. Now, again, I'm sure you know a lot about this, but some of the energy in the core of the sun is emitted as gamma rays. As this radiation gradually makes its way out through the very dense solar interior, it loses energy until it gets to an energy that emits invisible light. Now, this doesn't happen in a nice straight line like is indicated in this cartoon, but it's essentially a random walk. The photons don't know where they're going, they just randomly bounce into each other until eventually they get to the surface and escape as visible light. And that process in itself actually takes about 100,000 years. So in some ways, the light that we see today originated deep in the core of the sun about 100,000 years ago. Now, as I said, my work focuses mostly on the atmosphere of the sun. So I'm going to move on, okay? And this is again a picture of the solar photosphere, which a lot of you will be familiar with. It's where we can see the sunspots. And I'm going to play this movie. This is actually a movie, and this movie will go through different wavelengths which correspond to increasing temperatures and increasing heights within the solar atmosphere. Okay, can I play this movie? Okay. So running through this movie, I'll let it run a few times. So above the surface of visible light, we start climbing in temperature to a layer we call the chromosphere, where the temperature climbs first from a little dip to about 4,000 meters, gradually to 10 and then 100,000 degrees. And then ultimately we come to a layer called the corona, which is emitting in ultraviolet, extreme ultraviolet, and even X-rays. And the temperature there is well over 1,000,000 degrees. And this problem is known as the coronal heating problem, and I'll come back to that. Now, there is an image here where I want to pause briefly. Now let it start again, if I can. And let me drag it back, see if that works. And it's this black and white image. This is not so much an image as a measurement of the magnetic field on the sun's surface. And strong white and strong black are just areas of magnetic field pointing directly towards or away from you. Now, hopefully when I start the movie up again, you can see that these regions where the magnetic field is very, very strong actually also coincide with regions where there is very strong emission in these hot temperatures. So we've known for a long time that the regions of strong magnetic field correspond with very bright emission. We just don't quite know how the magnetic field manages to heat the local material. Okay, so this is just an image that summarizes the information I've given. On the horizontal axis here is distance above the photosphere, or the surface of the sun. And then on the vertical axis is temperature. And we climb from a temperature of just over 4,500. In actually a very short distance, we reach coronal temperature of more than 1,000,000 degrees. And this is known as the coronal heating problem. And why is this a problem? Well, it's because there is no direct source of energy. If we go down this way, a long way, we come to the solar interior and the nuclear core. That's where the nuclear reactions take place, and that's where the ultimate source of energy is. However, as we go out through the sun and then out into the atmosphere, really the temperature should go down because we're going away from this source of energy. And yet there is this steep climb in the temperature very, very rapidly to millions and sometimes even tens of millions degrees during a solar flare. Now, this coronal heating problem has been keeping solar physicists busy since the mid-1950s. And although we know a lot of the agents, we still don't quite understand all the details of how this process works. Okay, so I've already talked about the magnetic field. This is again a representation of the interior of the sun. And we know that there is what's called differential rotation. Not all parts of the sun rotate at the same speed. And that creates a layer where material is shared. And we reckon that's where a sort of dynamo resides, where the magnetic field of the sun is generated. The Earth also has a magnetic field, as I'm sure you all know, but we have an iron core, which generates a magnetic field. That's not true for the sun. So we reckon it's this shear layer somewhere below the surface where the field is generated. Now this is just a cartoon representation, but we think the field somehow rises through the surface. And because the surface layers of the sun also experience differential rotation, where the equator actually turns quicker than the poles, this magnetic field, if you can imagine this cartoon here, the magnetic field near the equator here would be dragged quicker. This is of course an exaggeration to explain it, but eventually you end up wrapping this magnetic field and tangling it up completely. And that causes a lot of the activity of the sun's cycle. Okay, so what happens locally? This is again just a cartoon representation, but what we find is that this magnetic field bursts through the surface and forms these huge magnetic loops. A little bit like a bar magnet represented on the side here. And the areas on the surface where the field bursts through, these are actually sunspots. So sunspots are regions where the magnetic field is extremely strong. Now, one thing I need you to remember for the rest of my talk is that the bottom or the feet of these magnetic field lines remain anchored below the solar surface, where all this convection is still going on. And that's something I'm going to come back to later. Now let's just for a minute talk about sunspots. So these are these areas of incredibly strong magnetic field bursting through the surface. And I've already said it's on the photosphere in visible light where we can actually see these sunspots. And I'm sure, as you know, sunspots have been observed for a very, very long time and actually get monitored quite closely. So this is a picture when the sun was quite active. You can see several sunspot groups on the surface here. And then on the side here is a zoom image of one of the best ground-based solar telescopes there currently are. It's not actually a picture of this sunspot, this is just to represent it. But you can see this incredibly fine scale structure, the dark part of the sunspot, which we call the umbra, or the shadow. And then you get this kind of hair-like structure almost extending from the side, which is called the penumbra. And superimposed on here, just to give you an idea of scale, is a picture of the Earth to scale. So when we refer to sunspots, they're pretty large spots. It's all relative, really. Now, outside the sunspots, I hope you can see this kind of honeycomb-like pattern of dark little lanes and then bright patches. Now, these bright patches and dark lanes are what we see on the surface of this subsurface granulation pattern that I mentioned earlier. So just below the surface, hot material rises up in large cells, comes to the surface where it then cools down and sinks back down in these darker layers or these darker lanes. So we get updrafts in the center of hot material, and in the edges we get downdrafts. So hot in the bright center here, and then downdrafts in these darker lanes. This is just a still picture of this convection pattern, but in the next slide, I will play the movie. Again, we see a sunspot, a really nice sunspot, but you'll see the movie zoom in on the convection pattern here. So here we go, gradually zoom in, and hopefully you can see that this surface is constantly bubbling and jostling around. And remember, the magnetic field is stuck in there. So you can already imagine this magnetic field isn't going to sit still and be in what we would call equilibrium. It's constantly going to be moving about. Okay, so I'm going to start telling you a little bit more now about the outer solar atmosphere, which we call the corona. So there are these huge magnetic loops that break through the surface. Now, magnetic field itself is of course invisible. However, the plasma in the sun's atmosphere is what we call ionized. So it's electrically charged, which means that it gets trapped. It essentially gets stuck to these magnetic field lines. So although we can't see magnetic field, what we can see is the hot gas trapped on the field, nicely outlining the field lines. And so on the right-hand side here is a picture of the solar atmosphere, the solar corona. The picture represents gas that's at about 1 million degrees. And you can hopefully see the superposition of lots of really nice magnetic loops. Excuse me. Now the solar atmosphere is full of these magnetic loops. This is just a picture taken a while ago in 2011, just before the last solar maximum. And so you can see that there's lots of collections of these magnetic loops all over the surface. And where we get a group or a strong concentration of these, we refer to these areas as active regions. So active regions form where you get two of these really large sunspots. And I'm sure you've heard of the sunspot cycle. So this is just a representation of time on the bottom axis, the horizontal axis, since the 1900s. And then on the vertical axis is the number of sunspots. And this goes up and down in a fairly regular cycle of roughly about 11 years. And we go through solar minimum when there are very few sunspots, up to solar maximum, and then up and down we go all the time. So the pattern is fairly regular, although you can see that sometimes the number of sunspots end up being much larger, sometimes it's a bit smaller, but we do go through these cycles. For the moment, we're actually near solar minimum. We're waiting to come out of solar minimum because usually we don't know that until we've seen sunspots of the right orientation emerging to call it a new cycle. So as the number of sunspots changes over time, you can imagine the active regions in the outer solar atmosphere also changes over time. And on the next slide is kind of a collation of images going from 1996, which was one solar minimum, through to a solar maximum in 2001, and back down to the next solar minimum in 2006. And you can see how dramatically the appearance of the outer atmosphere actually changes over time, from a very bright, active and dynamic sun to a pretty quiet sun during solar minimum. So for the moment, although this is a while ago, the sun looks pretty similar to this picture actually, and I'll show you right at the end. And the sun is pretty quiet just now. Okay, this is a movie and I'll take my time over explaining this. This is a full disk image on the left-hand side, again in a temperature of about 1,000,000 degrees. You'll see a little kind of zoomed in area here where you see a lot of detail of this active region. And in the bottom corner here is actually the surface magnetic field underlying this active region. So when I play the movie, hopefully this will work, you'll see obviously the sun rotating and we see we're following this active region. We can see how the magnetic field changes on the surface and how in response to those changes, the active region changes higher up in the atmosphere as well. And you can see that over time, although the general appearance of the structure of the atmosphere remains fairly similar, on a detailed level, it's constantly changing. It's actually very hard to pick out any structure that lasts for roughly more than an hour. So on that time scale, things are constantly changing. The magnetic field here is constantly evolving. It is partly still emerging for this particular active region, but it's also being pulled apart by the differential rotation as well as it rotates around the solar disk. So I'll let that play once more. And you can see how these connections between the two foot points are constantly changing. Now, let's go into a little bit more detail. I've spoken about these magnetic loops a few times now, anchored with their feet or their legs still down in these large convection cells. Now the movie, again, I'll play it just after I've explained it. The movie on the right is a movie of slightly cooler gas. We're talking about gas somewhere between 10,000 and 100,000 degrees here. And so this particular movie or image really only shows the lower legs of these magnetic field lines because the upper regions are hotter and they are not captured in this particular wavelength. So I'll play the movie and you can see, hopefully, how this material is constantly moving about and jostling because of this convection pattern. Okay, so don't think this is cut off here. It's not just little bits sticking up. It is really just the lower legs, and they do go up in these large loops, but that's hotter material that's not captured by this particular image. So this magnetic field is constantly moving, constantly jostling about. And that is actually something that we work on here in the group in St. Andrews. So I wanted to just give one slide about the work we do here in St. Andrews. What we look at is, I'm just going to go back for a minute and play the movie again. What we look at is how the constant friction and interaction of these magnetic field lines generates currents. And currents are a pretty close step to heating the plasma locally. So we know if we can generate large currents by all this jostling magnetic field, we can heat the local plasma. So one of the things we do, rather than model this really complex pattern here, is we break it down and say, okay, well, in which ways could you move these magnetic field lines around? One particular way of doing this, if you look at the black and the white patch, just imagine these are two patches of magnetic field, is you can move them past each other. So you can literally drag them and move them past each other. And don't worry about all the colored lines, but the kind of colored surface, the blue colored surface in this particular animation represents current. And you can see that as these magnetic sources are dragged past each other, then you get this spread out layer of current forming between them. And we know that will cause the local plasma to heat up. A different type of motion is where you take the kind of magnetic loops, which we tend to straighten out in our simulations because it makes things a lot easier. But if you imagine just twisting them around each other, you can see that again, this is meant to represent the kind of jostling motion of the foot points. You, in this case, this author, which is actually myself for this movie, has chosen purple for the current. The color doesn't mean anything, it's everybody's preferred color. My colleague clearly liked blue, I liked purple. Again, represents layers of current that get spread out throughout what would be this local fluid and heats it up. And then the last kind of elementary way of moving magnetic foot points is literally to just spin them. So you just spin them on the spot. See if I can play this movie. And in this case, the current sheet is red. No, that's not looping. We'll just play that a few more times. So you twist the magnetic field up, and again, you get currents generated locally. And so you get heating spread out throughout this plasma. So as I said, we have a fairly good idea of the basic principle of how to generate these large temperatures. And maybe looking at these movies, you think, well, what's the problem? Clearly they know how to do it. They can generate heat. What we can't do is do this on length and time scales that match the observations we have in the solar atmosphere. Our models all struggle mostly with the time scale, and our heating is far too slow. Because what these models that I'm showing here don't include is cooling, because the sun, of course, radiates. And if I would include the cooling is too quick in comparison to our heating models. So although we have a basic idea of the principles that are working in our sun's atmosphere, we still don't really have it all right. Okay, now, what I was showing you in the work we do here in St. Andrews are quite small scale motions. What can also happen in the sun's atmosphere is that this field gets tangled up and becomes very twisted, so tangled up eventually that it becomes unstable. And at that point, some kind of local explosion or instability happens, and that's what a solar flare is. So I'm going to play this movie, which is a local kind of magnetic field line here. Hopefully the movie will repeat again. And you can see that this local region here gets very, very bright just before the flare erupts. And that then afterwards, a whole load of material is ejected away from the sun into interplanetary space. So solar flares are essentially nothing but the local magnetic field becoming so twisted and stressed that it becomes unstable and erupts. Now, as that happens, as you can see in this movie, a lot of material is ejected from the sun, and these events are referred to as coronal mass ejections. I'll play some movies in a minute, but these are just still images. There's an image on the left here of a coronal mass ejection just about to take off. It's about to cut free from the sun's surface here. And just for comparison, the Earth is shown to size here. So again, these are huge structures of material and magnetic field being ejected out into space. The image on the right is taken with an instrument called a coronagraph. And for those of you not familiar, I will quickly explain. It's an instrument where the very bright disk of the sun is obscured so that we can see the much fainter atmosphere surrounding the sun. Okay, so this kind of solid region here is the actual disk of the instrument. And this little picture here represents the surface or the disk of the sun, but it's actually just superimposed afterwards. So all you would really see here is this disk obscuring the bright surface of the sun. And then you see this large kind of, but faint normally, outer solar atmosphere into interplanetary space. And again, sorry, go back, you see a coronal mass ejection just about to take off and start accelerating. So this movie is a full solar disk, and it again shows the start of a coronal mass ejection. I'll play it, and you can all try and spot where the coronal mass ejection is going to happen. Okay, so you can see again a huge ejection of material there. There's this structure here, which is hardly noticeable at the start of the movie. It sits there very quietly, but all of a sudden you see it starting to rise, first slowly, but then the rise phase accelerates until it eventually takes off and is ejected from the sun. Now, these look quite dramatic, but they are actually just a normal part of the sun's activity. And particularly near solar maximum, you can get up to about 3 large coronal mass ejections per day. So this is a movie from around the last solar maximum, around 2014. And the movie actually covers a few days. So it's of course very speeded up, but it's just to give you an expression of an impression of how regularly these large mass ejections, there's a few smaller ones happening, there's a few larger ones as well. And you can see they just carry on, basically. There's a few smaller ones here going off. There's another small one. And then a few larger ones as well. So on average, we can expect about 3 of those a day. They're being monitored and captured. In the background here, I'm sure all the astronomers have spotted the night sky in the background of the image here. So with 3 large mass ejections per day, and the sun of course is spherical, it's inevitable that some of those are ejected in our direction. So on the next movie, there is, it's unfortunately lower quality, this movie, I do apologize. But again, it's a series of coronal mass ejections that you can see, and you will see near the end of the movie what happens to our camera systems when one of these coronal mass ejections comes our way. There you go. Okay, I don't think that detector was particularly happy at the time. So as one of these events comes our way, a huge amount of highly energetic particles hit the detectors and saturate them briefly until they're passed. The object in the background, I'm sure you can all guess, is not a UFO. It is actually a planet going past that's too bright and makes the detectors bleed. So Earth-directed CMEs are part of what we call space weather that affected the near-Earth environment. What is also present is a continuous stream of plasma from the sun, which is referred to as the solar wind. And the solar wind was discovered by watching Comet Tails. So here is a comet, you can see its tail streaming behind it. And then as it goes past the sun, you nicely see the comet flip and its tail going in the other direction. Now at that stage, I will see if I can pause it. Okay. At that stage, its tail is actually blowing ahead of it. The tail is ahead of this comet in the direction the comet is going. And that told early observers that actually there had to be some kind of outflow from the sun that was faster than the speed of travel of the comet. A little bit, I'm sure living in the highlands, you all know this, a little bit like the wind blowing hard enough in your back to have a scarf or your hair blowing in front of your face, despite the fact you're moving in that direction. So we've known for a long time there had to be some kind of outflow from the sun. And this is referred to, this is kind of a gentle stream of plasma from the sun, which is referred to as the solar wind. And the solar winds, together with the coronal mass ejections, form what we call space weather. Now, space weather is present all the time, and the solar corona doesn't just stop somewhere. There isn't some kind of boundary. We actually live inside the sun's atmosphere. And we have our own magnetic field which protects us. So in this animation, it just kind of goes through explaining how this magnetic field is affected by the solar wind. So we have the Earth with a dipole field, essentially from the North to the South Pole. But because the solar wind is constantly gently pushing on one side, this field is not symmetric. It is squashed on the day side facing the sun, of course, and it's stretched out in a long kind of carried with this solar wind on the night side. And so it kind of sits there almost like a bubble, like a bubble protecting us, with most of the energetic material from the sun just streaming past us gently. However, as I'm sure you can guess, not all of it just streams past. Of course, our magnetic field allows for a little opening right by the poles. There's the North and the South Pole, where this energetic material can actually come down the local field lines. And the next movie, again, is a cartoon. It's made a little bit dramatic for effect, but it explains what happens quite clearly. So this is a cartoon representation of the sun and of one of these coronal mass ejections leaving the sun, traveling through interplanetary space, and eventually hitting the Earth's atmosphere. Most of it travels past, but you'll see that some of it actually comes down on the local magnetic field lines, and as I'm sure you know, causes the aurora. Now, I'm assuming that the eagle-eyed amongst you will have noticed that the coronal mass ejection hits us at the day side. And of course, that's not where we see the aurora. We see the aurora at the night side. So rather than just traveling straight down this field, the process of a solar storm is actually a little bit more complex. And it happens through what's called a substorm event. So you will see in the representation, I'll just try and catch it here, that actually most of the material, oops, that didn't work, flows past. Can I drag it? Yeah. Flows past, and then actually an event in the tail of the what we call the magnetosphere happens, which we refer to as a substorm, where these long stretched out field lines get pinched together, and at that stage high energy particles flow back to the Earth and hit the Earth's atmosphere on the night side, which is where we see the aurora. So here you go, high energy particles hitting the atmosphere, ionizing it and generating the aurora. Now, normally I can impress my audience by this picture on the left-hand side of the aurora in St. Andrews, but I'm assuming, speaking to an audience based in the Highlands, that you will have a lot better pictures than I actually have. So this was an aurora in 2003, when in St. Andrews we were lucky enough to see the aurora night after night for quite an extended period. Now, the aurora is, of course, always there, we know that, but during a particular energetic solar storm, field lines slightly further south from the normal auroral oval get energized, which is when we in Scotland can see or enjoy the aurora as well. Now, this is the nice part of solar storms. There is a more dangerous side of solar storms as well. Because a lot of energy comes down, this has the potential of affecting technology on Earth, particularly long metal structures. And structures like that, where it can induce currents. So structures that I'm sure you can all think of that are relevant to us, particularly in Scotland again, are pipelines, train tracks, power lines. And out in space, just before the kind of low orbit space surrounding the Earth, of course, all our communication material, radio signals, satellites, and I'm sure I don't need to explain to you how much we are relying on satellite communication these days. Mobile phones, this Zoom meeting, GPS tracking can all be disturbed through solar storms. Now, most of it'll just be a gentle disturbance, but occasionally things go wrong. And the pictures on the right-hand side are, maybe you've recognized, of North America. If you can probably recognize the Great Lakes here. And this is the northeast coast of America, going up into Maine. And you can see this is a picture, a nighttime picture of the lights on the northeast coast of America before and after the solar storm. And you can see that a large chunk of the lights have gone out, and about 6 million people without any electricity back in 1989. And on the other side of the world, a local gas pipeline explosion essentially demolished part of the Trans-Siberian Railway and killed a lot of people. And again, that event was eventually related to a large solar storm in 1990. So those are the less pleasant effects. What can we do about this? Well, a lot of it can be caught by technology, by having redundancy in our both communication and power stations, but some of it we can't anticipate. One of the things we can't anticipate is the amount of damage actually done to the solar panels of our satellites and short-circuiting the equipment on board as well. Now, what's particularly relevant these days as well is space travel. And I'm hoping that I can explain the picture on the bottom right here. Astronauts are just outside the best or the most protective part of the Earth's magnetic field. And that means they're no longer shielded from these high energy particles. And that's essentially the same as having a continuous X-ray done to you, which an X-ray doesn't do anybody any damage, but if you sit in it continuously, it isn't very good for you. Now, how does this affect space travel? On the bottom of this figure here, I'm not sure if you can read it, but it's essentially time from 1965 till about 1975 on the other end. The arrows here are when the Apollo missions to the moon happened, from Apollo 11 to 17, with a gap here for the unfortunate Apollo 13 mission. And the spikes, the black spikes on this image represent particularly severe solar storms. Now, if you look carefully, you will see that each of these arrows by miracle missed the large solar storms. There's some smaller ones in between, but they missed the major one, particularly this one here and this one here. Now, going to the moon and back again takes about 10 days for a trip. And so the odds on missing a major solar storm are pretty good. And I must say here, this was not by anybody's careful timing that these Apollo missions missed these large solar storms. This was just good luck. If we really want to go to Mars, that trip takes about 180 days. And at that point, you have no chance of avoiding a major solar event. There will be one during that time. And in addition, Mars itself has no, or at least a very, very weak magnetosphere, which is the magnetic field surrounding a planet. So even once you get to Mars, to be honest, I don't particularly fancy walking around there because you will have no protection from this high energy solar material that's being sent into space all the time. So this represents a particular engineering challenge is how to protect a spacecraft from these solar storms. Now, for the moment, we have the International Space Station, which is currently, which is of course always there. The astronauts stay there for a long time, but we send the astronauts warning when a particular storm is going to hit. And they actually have a special room that is lined with lead where they can retreat during a bad storm to protect themselves. Now that's okay for the International Space Station, which essentially we've built there and is in situ, but you can't really launch a spacecraft made out of lead. That would be probably too heavy and also cost too much fuel to get to Mars. So engineers are trying to see if they can recreate a magnetosphere around some kind of spacecraft, whether it can have its own small magnetic field to protect itself. Now we can generate a magnetic field that is good enough, but for the moment, the magnet we would need to do that is still larger than the spacecraft. So not a solution, but if you have any budding engineers among your acquaintances, then please encourage them to study space engineering because we need them. And with that, my talk is actually nearly at an end. I wanted to leave you with these pictures of the sun. This is actually the sun today in a range of different wavelengths. The large image here in the middle is a wavelength corresponding to about 1,000,000 degrees. Up on this side are slightly hotter wavelengths. The bright orange one here is about 1.5 million degrees, and the pink one is about 2 million degrees. On the left-hand side, the kind of boring looking gray image is the visible light solar surface. And you can see that unfortunately there are no sunspots whatsoever. At the top here, we've got the magnetic field, and you can see there's a little bit of magnetic activity here, which corresponds to this region on the disk here. These images are kind of in between. So this is about 6,000 degrees, about 10,000, and going up to about 100,000 degrees. Now, just before I finish, I wanted to highlight this particular image. This image is in about 1.5 million degrees. And this particular wavelength tends to show us where there are coronal holes. Now, coronal holes are regions where the magnetic field is open into interplanetary space. And normally they happen near the two poles. So you can see there's a nice coronal hole at the pole here, and there's a little bit one here at the South Pole. But sometimes you also get one near disk center, near the equator. And you can see there's a faint, it's not a large, but there does look like a bit of evidence here of a coronal hole. And now when there is a coronal hole near the equator, we sometimes also get to see the aurora at lower latitudes without the need for a large coronal mass ejection or solar storm. So if there has been some faint auroral activity in recent days near you, then I suspect this might be related to this coronal hole on the disk center here. And they'll be with us maybe for another 2 or 3 days before they rotate too far away. And with that, my talk is finished. I'm very happy to take questions. And I think I will stop sharing so I can hopefully see everybody else again. Thank you very much.
Well, hopefully you'll be able to see me. Thank you very much indeed, Inika. That was absolutely fantastic. I've got a rake of questions here. We've got about 10 minutes, 15 minutes allowed for them, but we'll try and crack through as quickly as we can. The first one I'm going to pick up is from Eric. Why do the magnetic fields swap over when solar sunspot cycles change?
That is such an excellent question, and I wish I could answer it. We partly know. So over the 11-year cycles, the sunspots start emerging at higher and higher latitudes. And sunspots are tilted in a particular way. You can imagine the plus and the minus are slightly tilted. They eventually merge higher and higher near the poles, and they cancel the field near the pole out. So if you imagine, say, the pole is a plus sunspot would be orientated with the minus part of the sunspot group, because there's always two of them, closest to the pole. And eventually enough of these minuses cancel the plus field near the pole, and then you end up reversing it. So you're right, the solar cycle is 11 years, with the field reversal taking 22 years. So every cycle it reverses, so it takes 2 cycles before we're back to where we started. So that's a very crude explanation where, again, we have what I would say is a cartoon level understanding of the process. What exactly drives this process and why the cycle is 11 years and not 15 or 9, we don't know. We do know that other stars have cycles as well with different timings, some are less, some are more, but we don't know what causes the cycle, the actual timing of the cycle.
Okay, picking up on somebody else's question, very recent one. If you have your cycles of 11 years, 22 years, are there longer cycles that are in the background?
Yeah, absolutely. There are several longer cycles. The best well-known is a 100-year cycle, and I believe there's also a 200-year cycle. I do think there might be longer ones as well, but I don't know much about those. But there are definitely longer term cycles as well. You can probably, if you remember from my picture of the sunspot cycle, the cycles seem to be slightly stronger around the 1950s, 60s, 70s. So that was part of a kind of longer term cycle overlying the 11-year cycles, where for the moment the cycles are slightly weaker than they have been, say, about 30, 40 years ago.
Okay, doke. Thank you for that. A quick one from myself. What is the mass of a typical coronal mass ejection?
Oh my goodness, what a good question. Now, I could quit this presentation and look for it, but actually I don't know the number off the top of my head, but they are large.
Mm-hmm. Well, it relates to a question that comes from Tracy. Why does the sun's gravity not pull back the CME before it escapes?
That's an excellent question. The sun's gravity is actually not all that strong, but essentially these CMEs have a velocity that's bigger than the local escape velocity. So they really are flung away from the sun at a pretty high speed. The speed of a CME is of the order of about 1,000 kilometers per second.
Aha, okay, I understand that. Changing topic then, David Davidson has said, I've been trying to find out an answer to why the sun is darker at the limbs than it is at the center as we view it. I would have thought that a gas ball would exhibit just the opposite.
Oh, okay. I'm not sure I can answer that. Can you read the question out again? I mean, I can only see.
It's if you look at a typical illustration of the sun, it will show the limbs as darker than the center as you're looking at it. David wonders that he would have thought that a gas ball would exhibit just the opposite.
Yeah, I can only imagine it's just not emitting in the right direction.
I think to help you out, I think that is the answer, that the light has to transit through other layers to get to us, and it loses a bit of the energy as it goes.
I mean, one thing to keep in mind, although I show all these lovely images, the density of the number of particles in the outer atmosphere is extremely low. I was always told, not that anybody has tried this, that if you actually could go to the solar corona and stick your hand in it, you would not burn your hand, because the chance of a particle actually hitting it is almost zero.
Mm-hmm.
So there isn't actually all that much material there that's emitting.
Okay, let's turn to a question from Sigma. How big a part do the recently discovered nano flares play in heating the solar corona?
This is obviously somebody who knows what they're talking about. Now, I could give an entire talk about this, but we'll try not to do that. So nano flares are, to some extent, a theoretical concept. They are a small energetic event that we can imagine will happen with an energy a lot smaller than a flare. And we think they will happen very locally. Now, there's a bit of a, nanoflare is a bit of a catch-all for an event that releases heat. We still don't actually know what nanoflares are. Are they caused by waves propagating along the magnetic field? Are they caused by small reconnection events of the field where the field is locally tangled up, but not on a large scale to cause a flare? So we refer to nanoflares a little bit as a kind of catch-all local small heating event. Now, there is a big debate in the solar community that's still ongoing, whether you need lots and lots of small nanoflares throughout the atmosphere to heat it, or whether it's enough to have less but larger events. And that's not an easy question to answer. But nanoflares, whatever they are, probably do play a big role. It's just that we don't actually really know what nanoflares are. It's just a theoretical concept of a small flare.
Okay. One from Eric. We're talking now about the energy getting as far as Earth. Are people living closer to the auroral oval areas, the North and South Pole areas, more at risk from the effects of extreme solar storms?
God, again, that's a good question. I think the answer is yes, in the sense that these disturbances will, of course, happen more often, but I assume they're prepared to deal with it. Now, most of the auroral activity actually happens very high up in the atmosphere. So certainly transatlantic flights, for example, will fly a different route if we know that there is a lot of solar activity, which is not in the normal auroral oval. So most of the activity actually happens very high up in the atmosphere.
Okay, good. One from myself. We have a number of spacecraft that can alert us to an incoming coronal mass ejection. Can we react quickly enough to minimize infrastructure damage?
No, not really. And this is one of the large research areas within solar physics. The problem with a coronal mass ejection that's Earth directed is that it doesn't form this kind of nice bubble that you see shooting off to the side, because the bubble is coming towards you directly and is actually very faint. It is very hard to detect. And even once we detect it, we don't have much warning. We have 8 minutes, in fact, which is not a lot to protect our equipment. So one of the so there are several things we are doing. We now, as you say, have several satellites monitoring the Sun-Earth line. We have a few satellites which have started to leave the direct Sun-Earth line so they can look at it side on when CMEs are easier to detect. So that should give us a little bit more warning when a CME is about to happen. But a lot of theoretical work is going on as to try and identify regions that will erupt before they erupt. Ideally, up to a day in advance. That's when we give people proper notice. Then people could turn satellites around, fold the solar panels, switch off electronic equipment if needed. But we would need about a day's warning. And we are trying to identify structures that will erupt. For the moment, the best mechanism to identify regions that are going to erupt are still human beings. People who are trained and who monitor the sun a lot are still our best bet at predicting. And we still don't really know why we can't actually teach the computer. For some reason, humans are just better.
We are superior. That's the word you were struggling for. Very good, Inika, but thank you very much indeed. I think we'll call the question and answer to a halt there, and I'll hand back to Eric, if I may.
Well, Inika, I would just like to take this opportunity to thank you for a most interesting and inspiring talk. I observe and photograph the sun through my wee hydrogen alpha scope, and it's now going to mean a whole lot more to me, as you've helped increase my understanding of the many complex processes that are actually going on. However, I'm now a wee bit more apprehensive of the circumstances leading up to extreme northern lights now. So we'll see how that goes. Anyway, Inika, normally you would be receiving a token of our appreciation and a thank you card designed and printed by Pauline to a rapturous applause from the audience. You still will get to receive those things, except we'll need to work out a way of getting them to you, but I'm sure we'll do that. I can't do the rapturous applause thing, but Inika, thank you so very much once again.
Thank you very much for inviting me, and I hope you enjoy the rest of your meeting.
Thank you, Inika. And now to the club news, astro picks and targets for the month. Pauline is with us this month and has another wonderful and informative presentation for you. Pauline, over to you.
Thank you, Eric. Eric has already spoken about Arthur in his introduction, but he wasn't able to show any photographs and asked that I would show you some here. And this is one of the earliest photos of Arthur taken in 2002 when we were renovating what was to be our JSL Observatory Mark I. You'll recognize this photograph of Arthur cutting the 20th birthday cake for Haas. He has been with the Society for virtually all those 20 years. And some of you remember chatting with Arthur in the early days of the Spectrum Centre. Here's Arthur at our 25th birthday celebrations with Howie Firth. And this photo shows him at the observatory at 89 years old, helping to postcrete the new fence posts to hold up the badly tilting fence. He would always offer to help whenever he could, and we had to often remind him to slow down. He was a gentleman and a true gentleman, and he will be greatly missed. And I just want to reiterate my thanks too for all the tributes that you have sent, so that I have put them onto a card, and that is on its way to Lorna. The constellation this month is Borealis, and the two dots over the second O indicate that both O's should be pronounced separately as Borealis, and I shall continue to try and pronounce it properly. Now, it is at its best late summer, but also springtime. Many would argue that it might be leaving it a little bit late to view at this time of year, as it's gradually sinking into the western sky. However, its bright star, let's get the laser pointer sorted, which is Arcturus, is easily visible after sunset as one of the first stars to appear. And sunset can be used as a good pointer to where Borealis may be found. Another pointer, of course, is the Plough, which is high enough in the sky at the moment to follow the arc all the way down to Arcturus. And although Arcturus will disappear perhaps by the end of October, the top half of Borealis is actually circumpolar. And Arcturus will return in the early morning skies from October, and it'll probably be late January before we see Arcturus at a more decent time of night, maybe around 10 o'clock or so. Now, the constellation itself looks more like a kite or even an ice cream cone than the figure it is supposed to represent, which is a herdsman or ox driver. The name Borealis means both herdsman and ox driver. Early civilizations thought it resembled the torso of a human with a raised arm, and you'll notice that in the previous pictures we didn't see this part of the constellation, and it's the same with all constellations. They will draw them very slightly differently. So many drawings show him with a sickle, as he may represent the person who first taught ploughing and agriculture. More recent illustrations show him holding both a sickle and the leads of his hunting dogs, Canis Venatici, not to be confused with Orion's dogs, Canis Major and Canis Minor. So this is Canis Venatici, which only really has a couple of stars in the constellation. This looks like something out of, I don't know, Doctor Who or science fiction movie or something. In fact, it's supposed to be Comet Tails, which is hair. He may also be depicted driving the oxen which pull the wagon, delineated by the plough, as you can see here, around Polaris in a great circle. Some stories even suggest that the oxen are tied to the polar axis. So that would be pole star here, the last star in the tail of the little bear. And it's this movement that keeps the skies in constant motion, which I think is a really lovely way of looking at it. You'd have to drive the oxen down, as in here, so they would have to go down and around in order to make sure that the plough moves the correct way around the pole star. Other legends saw him as a keeper or driver of bears, and Arcturus actually means guardian of the bears. And with his two hunting dogs, which unfortunately is not shown here, he chases the two bears around the pole, which of course is here. Exactly who Borealis represents is really unclear, and there are many myths and legends from around the world involving Borealis, Ursa Major, or the plough. And that is something that you can look up for yourselves. Otherwise, I'll be here half the night talking about all these stories. Now, the brightest star in Borealis is Arcturus. It has a magnitude of minus 0.05. And as soon as you get into the minuses, you know you're looking at a bright star. And it is, in fact, the fourth brightest star in the sky. It's an old K-class giant star, 27 times as large as the sun. And you can see the size of the sun here. It has a low surface temperature of 3,900 degrees Celsius, which is why it looks orange. And it's an old star, so it is an orange giant star. Now, it's actually known by and is important to very many civilizations across the world. And thus it has a lot of different names. Other stars range in magnitude from 2.5 to 4.7, and a number of those stars making up the constellation, as well as a few within the constellation area, are actually double or multiple stars. Although a few of these doubles or multiples can be seen with binoculars, if you want to see the different star colors, that's always better achieved through a telescope. So there's Arcturus, and these stars are actually easily visible, because I had a look last night. We had a beautiful clear night last night, and yes, I can definitely see all of these despite the full moon beginning to shine quite brightly across the sky. Now, I'm not going to go through all the double and multiple stars. What I've done is to divide them into sections, and I'll simply mention those that are worth looking at with binoculars. So we have Delta, which is a double star, and I could see that last night. It's a fairly wide double. Mu I couldn't find, and that has a wide binocular companion, so that's easy enough. And then we have this star here, Epsilon, that will need a telescope to actually separate the components. the main components, and you'll need a good telescope with a much higher power in order to split the fainter of them, which gives you your triple star. But this is known as Isar or Pulcherima, which means most beautiful, because it's a little bit like Alberio. It has this wonderful color contrast of a yellow orange and a sort of a greeny blue color. Sigma and Rho you can see with the naked eye if the sky is dark enough. Mine wasn't. I could just see Rho, but I could see Sigma through the binoculars. And then these two stars I couldn't find, but in order to split them, you do actually need a telescope. For the main components, you need higher power and maybe even a medium-sized telescope in order to see the other components that make up these triple and multiple stars. And then the raised arm of Boötes consists of 3 faint stars, which you can see here, and 2 of those are multiple. But the best way to find them is to look for Alcade, which is the last star in the plough. And then it's an easy hop across using binoculars, and you can pick these up really easily in the binoculars. So Kappa, you need a telescope to split this one, but Iota I could see quite easily with binoculars. However, the third companion, once again, you'll need a telescope for. And while you're in the vicinity of Boötes, if you go to Delta, very close by is this little constellation here called Corona Borealis. It means northern crown, but it actually looks like a necklace. Now again, sky was washed out by the moon, so I couldn't see the faintest stars, but I have seen this in a dark sky, and it really looks very pretty. Perhaps the only object worth looking at through a telescope, unless you've got a very big one with high power, because there are a few galaxies in Boötes, but they are not very bright at all. But this one is NGC 5466. It's a globular cluster, believe it or not. It's a little bit different looking in that it's fairly loose and it looks more like a rich open cluster. Through a small or medium telescope, it looks like a mottled haze, and a larger telescope is required to make out individual stars. Surprisingly, despite being a magnitude 9, it is quite dim. However, there are a number of decent deep sky objects to view, and these are just over the border of Boötes. And you can see that most of them are galaxies, but we do have 2 globular clusters. This one isn't brilliant, you'll need a telescope for, but M3 you can see with binoculars because it has a magnitude of 6.2. And what you do is you draw a line between Arcturus and Cor Caroli, which is one of the 2 stars making up the Canis Venatici constellation. You can find this star quite easily with binoculars, but try as I did, I could not find M3, but perhaps by that time the sky was just too bright with the moon. Now, there are 3 meteor showers that emanate from Boötes. The quadrantids are the best, peaking on the 3rd and 4th of January with about 100 meteors per hour, but unfortunately, they are rather faint. And then there are a couple of minor showers late January and June, which probably not really worth looking for. And do you remember me talking about the Hercules Corona Borealis Great Wall that was within the constellation of Aquila? Well, apparently it's so big that it takes up a significant part of the Boötes constellation. And not only that, but through quite a distance away through Boötes is the void, Boötes void. And this is a 250 million light year diameter void. It's not completely empty, but it doesn't have these huge superclusters and probably very few clusters of galaxies, if any at all. Now, if we look at our sky map, and I will include this when I send the information about the constellation, we've got Jupiter and Saturn, which still dominate the southern part of the sky. We can now see Mars, and it's already up by early September at 9 o'clock. So it should be in the sky by 9 o'clock, by this time of night. However, it looks better as you let it get higher in the sky. And we've also got, of course, Borealis, the constellation itself. So this will tell you where to look for it, sinking down into the west-northwestern sky, Coronal Borealis, and Canis Venatici here with M3. So it'll give you a chance to check out those bits and pieces. And Jupiter has a couple of new white spots have been found on Jupiter. One by Clyde Foster in South Africa, and then it was really fortunate that just a few days later, Juno went past and photographed this new white spot, which is really rather impressive. And then in August, an amateur astronomer called Ayasu Miyazaki from Japan found yet another white spot, and that's where the white arrow is pointing. And this might indicate an outburst or an outbreak of storms in the northern temperate belt. And the BAA would like any observations. Mars is now brighter than Sirius, which of course is the brightest star in the sky, although we don't see Sirius until into the winter time, beginning of the winter. It rises earlier every night, and it's getting brighter and higher in the sky as the month goes on. And I found this graphic on the internet which shows how the South Polar ice cap, and note this is a 3-month jump here, but it just seems to fade really quickly as Mars turns its southern hemisphere towards the sun. Mars will be close to the waning gibbous moon on the 4th, 5th and 6th of September. So if you haven't seen Mars yet, not sure where to look, find the moon on those nights and you will find Mars. I actually saw it for the first time last night, and my goodness, it's bright and it definitely looks red. Venus still shines like a beacon. Look out for the waning crescent moon in the morning sky, that is before sunrise, because Venus will be close by. And this takes place on the 13th, 14th and 15th of September. Now, interestingly, this is a graphic from somebody in America, a bit further south. This is a graphic from someone in Britain. Look at the way it's orientated. So you need to turn this by about 90 degrees. But basically, 14th of September, you're going to have a photo opportunity with the crescent moon on one side, Venus on the other, and the beehive cluster in the middle. You can see this quite well, or quite clearly, with binoculars. But you do have to get up at around 3:30 in the morning. I am not a morning person, so it won't be me. And the BAA would like photographs of the atmosphere of Venus if you happen to be able to take any. Now, look out for the aurora. It's something that Inika was talking about tonight, because it is in fact more likely to be seen around the equinoxes. So September and October are good months to see it. And the autumnal equinox is the start of autumn in the northern hemisphere. This is when day and night are of almost virtually equal length. And this is a time when the Earth's axis, now it's still tilted, but the whole thing is perpendicular to the sun. In other words, it's not tilting towards the sun as it would in the summertime, and it's not tilting away from the sun as it does in the winter time. And this allows, therefore, the same amount of sunlight to reach the entire Earth. And it sets up a special orientation of the interplanetary magnetic field and the Earth's magnetic field. So the interplanetary magnetic field is the sun's magnetic field after it has extended out into the solar system and enveloped all the planets, hence the name interplanetary. And it can point north or south, whereas the Earth's magnetic field only points north. Think of the compass. If the interplanetary magnetic field lines point north, not a great deal happens. But if they point south, then the two fields, that is the interplanetary magnetic field and the Earth's magnetic field, are of opposite polarities, like the opposite poles of a magnet. And they will connect, that is the interplanetary magnetic field with the Earth's magnetic field. This opens a door or even a crack in the Earth's magnetic field, and that allows through the solar wind, which then can spark off aurorae. But it's during the equinoxes, when the Earth's axis is perpendicular to the sun, that this orientation means that our planet's magnetic field is lined up really nicely with the interplanetary magnetic field. There's no tilt there. And the two fields are much more likely to connect, and connect far more strongly whenever the interplanetary magnetic field faces south. And this results in the solar wind being driven a lot more strongly towards the magnetic poles. And often these aurorae are not predicted, but they occur anyway, as the door or the crack in the magnetic field at this time of year is more likely to be open. That's how I understand it, but reading it is actually quite complicated. But it's something to do with the fact that the orientation means we're much more likely to see the aurora, which is great stuff for us. Now, I'm just going to mention the Orkney Science Festival. Eric sent me some information, but what you do is you go to this website here, you select what's on, and this allows you to browse the program by date or event type. And Eric has sent me some information that, or some of the activities that are going on that have astronomy in them. So there are a number of lunches. Every day there is a lunch when our Eric Walker will be talking about something in the sky. On September the 4th, which is Friday, we, Sigma, are hosting a visit from Professor Ken Rice, talking about the discovery of extrasolar planets and the speed of the discovery. And then that evening, it's about Orkney night sky for beginners, and Eric Walker will once again be talking about that. Lots of lunches planned for each day, and Eric is speaking on something each time. There will be other people speaking at lunch, each doing their own little thing, and Eric will be talking astronomy. So lunch again, lunch here, and then on September the 8th, Aberdeen Astronomical Society will be having a talk from Neville Brown about the building of the 3 great observatories in America. All right, so this is my favorite bit. Here we have your gallery of photographs. And of course, now the skies are getting darker earlier and earlier. In fact, the month of September, around the time of the equinoxes, it seems to gallop ahead. So it gets dark really quite quickly now. And it gives us a chance to see the Milky Way, which is what Dave has here. And once again here, so he's called it Starry Night, but this is the Milky Way, the beginnings of it. And very artistic photograph here. And of course, whenever we see any shots of the Milky Way, you see Jupiter and Saturn. And these are really quite atmospheric, some of these, they're beautiful. And I just want to point out, not just Jupiter and Saturn, but if you look here, if you remember from last month when we were talking about the constellation of Aquila, and I said to be sure that you're looking at Altair, check there's a star above, and if you've got dark enough skies, you can see a star below. That is the start of Aquila. There are the eagle's wings. There's his tail. This is Vega. You can just about make out the constellation of Lyra. And then we have Deneb up here, so which is the swan, of course. So we have the summer triangle just here. And as we go on, we've got a little bit more processing with the Milky Way. It shows how much detail can be brought out. And here we've got a meteor. Now, remember this photograph because you'll be seeing it again a little bit later on. Here we've got Mercury, the day after I said getting to the end of the chances of seeing all the planets in the sky at some point overnight. So well done, Dave, for getting this photograph. Venus at gibbous phase. And then we also have Venus rising over Tynwald in North Ronaldsay. So this is North Ronaldsay Astronomy Group. And this is a photograph by Sue Shackleton. And well done, Sue, for getting not just Venus, but also noctilucent clouds, which must have been just at about the end of the season because this was the 7th of August. Mars, which is a fabulous photograph here, and this is it made a little bit larger by Dave. This is Mars and the moon. Remember that photograph? So there's Mars and there's the moon. Notice that they are in a pretty straight line, and this was the 8th of August. On the 9th of August, the day after, Sue Shackleton took a photograph of Mars and the moon. Can you see there's a difference now? Because the moon rises later every night or every time. And here we've got Mars hiding in the corner with the Milky Way. And I love this beautiful full moon. And of course, one of Dave's specials, a close-up of the moon. This is mine. I captured the sunspots while they were still there. Obviously, they've gone again. Can hardly see them, so this is a magnified image. And then we have M103, which I think, Dave, is this one. I hope I'm right. And this is one of the stars of Cassiopeia, because M103 is an open star cluster that you find in Cassiopeia. We've got M31, the Andromeda Galaxy. This is M110, 110. And I think that is M32. And this is the little dumbbell. This is M27. And you can find this if you draw a straight line between Altair and Deneb, go back to that Milky Way picture, then M27 is about a third of the way up. So that's where it is. And lastly, we do have the beginnings of the aurora season. This is a lovely photograph taken by Ian Hall of North Ronaldsay. And indeed, we all need to get out there and start looking for the aurora. So for your bingo card, find the constellations of Aquila and Boötes, add them to the bingo card. It would be interesting to count the stars if you can see them, making up the outline of the constellation, as it then give an idea of local light pollution levels, but make sure your sky is dark enough and without a moon interfering. Also, put on seeing the aurora. So your bingo card is now growing. There are quite a few things for you to look out for. And I thought I would just leave you with this in order to finish. So that's me finished, and I am going to stop sharing. Here we go.
Absolutely wonderful, Pauline. That is just fascinating. What a work. And I see we're all putting a bit of humour into our presentations now.
Well, I had to. Oh, heavens, I am stuck. Oh, there we go.
Don't worry about
Trying
it.
to get rid of it. It won't go.
Ah, just absolutely
Well, I
fascinating.
have a high bar to follow after Gail had that bit of humour, so I thought, well, I better do something. Anyway, there we go.
Yeah, that was just great. The Orkney Science Festival, as Pauline was talking, was cutting and pasting stuff into chat. If you want to get the details, just go into the chat, select all, that's a Control A, copy it all, Control C, and then paste it, Control V, into whatever Office software you use, and all the links will come over as well.
I can also put that into the information that I send out to everyone about the constellation.
That's fine, Pauline. And I've actually, today I set out all the links properly. So I'll get that to you and then we'll get that to our members and friends. No problem. What was I going to say now?
Sorry.
Yes, I will get all that to you. It will be after the Orkney Science Festival. I'm rather a wee bit busy at the moment. And I'm also seriously looking forward to the proper start of the observance season. You saw some of the things Pauline has given us a target for. I cannot wait myself to get into observing the night sky. Now we've got a little bit of time, and if any member or guest has any questions for me or comments, just put them into chat or Q&A, and Paul will hopefully gather them up and present them back to me. Rona Fraser has reminded me that there are also the British Astronomical Association autumn webinars this Saturday, the 5th. So if you want to find the details of them, go onto their homepage and you can click on the link and you'll get into those webinars this Saturday. There's Paul. I see Paul back.
Yep, I'm here. I managed to press the wrong button and got rid of everything. I couldn't even find how to get back, but here I am.
Nothing like a little bit of adrenaline.
Nope. To stand by, there's one question coming up. It's from Steve Ashbolt. When do you think the first live observing session will be broadcast?
Hello, thank you for that, Steve. I am really hoping to get our first observance session broadcast before the end of September. The Science Festival finishes on the 9th. I'll have a day's rest and then I shall work with the team and we'll get a little observance session planned, and you will be informed via email, Facebook, the website, all the usual, and we'll make sure we get it going as soon as, because I am really keen on getting this up and running.
That's the only one. Oh no, stand by. There's another one. Steve says, "Awesome, thank you. Looking forward to it."
Aye, most welcome.
There you go. All right, Eric, we're finished, I think.
Okay. Well, everyone, again, thank you for another fantastic night. I enjoyed the talk. I enjoyed Pauline's presentation. Good interaction, good questions. So until the next meeting, clear skies, keep looking up.